Okay, this is going to be looking at graphs part 2. We did a part 1 where we looked at this graph, breadth first search, depth first search, and some vocabulary related to that graph. Alright, we'll start with a new example here. We have a list of things to look at. We're not going to do that here. Alright, so this is a graph. It's one of the examples that we were looking at in one of our assignments. One of these graphs. But anyway, here it is. This is a directed graph. The edges have arrows. So you could think of these, if this is cities are vertices, or intersections are vertices, and roads are edges, and these could be one-way streets. If you think of this as a friend relationship where the vertices are people, then the arrow could be likes. In any event, this is a directed graph. It's also a weighted graph. The edges have weights on them, so not all edges are equal. If this is a likes graph, then it could be the amount of like or dislike. The set of vertices here is V0 up to V5. Those are the labels. The edges, since they're weighted and directed, so we say this is the source vertex, and then where does it go, and what is the weight. So V0 to V1 with a weight of 5. If we're looking at an adjacency matrix, this is already filled out. So the first row here are the edges coming out of V0. There's an edge going to V5 with weight 2. That's listed in the last column there in the adjacency matrix. And then there's a edge to V1 of weight 5. Alright, since this is a directed graph, it's not the case that the first row is the same as the first column. With an undirected graph, the rows and the columns, you could interchange first row, first column, because that's true for undirected graphs, but for directed graphs that's not true. For V0, we just have the one edge coming in from V4. In a directed graph, you can talk about the total degree, which is all the edges coming in or out. You could also talk about the in degree and the out degree. Looking at V2 here, the number of edges coming in, there are 2, so the in degree is 2. The number of edges coming out is 1. And we could do breadth first search on this graph. The difference between this graph and the previous example that we looked at in the previous video, the edges have a direction. So if we start, this example was worked out starting at V2. If you do breadth first search from V2, you go to V3. That's the only edge coming out. And then from V3, you would go to V4 and V5. From V4, you would go to V0. And from V0, you would go to V1. And if we're taking into account the edge weights when we're doing this breadth first search, then that would go into the distance here. And you would, just like in the previous example, you would keep track for each vertex that you get to. So V0, how did you get there? If you do the breadth first search, you'll get there from V4. V4, how did you get there? Got the V4 from V3. And V3, we got to V3 from V2. Alright, so that is a directed weighted graph. I'm going to close that and start looking at another example. Call this graph 3. And what we'll do for this graph is we're going to do Dijkstra's algorithm and maybe Prim's algorithm. This graph is a weighted, undirected graph. And Dijkstra's algorithm supposed to compute the shortest path from some vertex. Let's say that we're going to start with G to all other vertices. And the basic idea is that we're going to start going out from G. So it's a greedy algorithm. Start paths out of G that are smallest. Okay? And that's the order that we consider the vertices in. We're going to have some information to keep track of. So for every vertex, we're going to have some distances so far, and some distances so far and parents, and I think we'll put that in as a table. So how many vertices do we have here? We have 8. So we'll put in a table with 8 by 3, I think we'll do. Put this down here. Alright, so we have A, B, C, D, E, F, G, H. Alright, maybe we'll have one more column. Alright, so this is the vertex. We'll have the distance and parent. So how did we get there? We're going to start from G. So we'll have the so we'll start from G, and G is going to be the source, so we'll put a distance of 0, and we'll put G as its own parent. Everything else, we will put a distance of infinity, which I'll just leave blank to mean infinity, and a parent of nothing, of nil. Alright, so initially we'll just leave those blank to make it look better. And then what we're going to do each time is we pick the smallest. We'll have a done list as well. So we pick the smallest pick vertex, smallest distance to it, that is not done. And let's see what we do. Alright, initially we don't have anything done, we just initialize the table like this. Okay, so now what's the smallest one that's not done? That's G. So we're going to pick G, and we're going to move it to done, and we're going to update all the neighbors of G. Alright, so from G we could get to F with 8. That's better than what we have, which was nothing, so we can get to F with a distance of 8. We can get to C with a distance of 9. Going through G, we can get to D with a distance of 7. Going through G, we can get to E with a distance of 2. Going through G, and we can get to H with a distance of 3 going through G. Okay, that's all the neighbors of G. We've updated them all. A and B are not connected to G directly. So the next step is we're always going to pick the vertex with the smallest distance that isn't in my done list. Which one is that? Maybe I'll highlight these when they're done. Alright, so the next one is E. That's the smallest. That's going to go on to the done list, and then I want to look at the neighbors of E to update them. Okay, I could get to D, so if I go from E to D, that's a distance of 3 plus the distance that I have to E. That's better than what I had before. So I should do that. I'll replace that with a 5, and I went through E. Going back to G isn't going to help. I'm already done with G. Going to H, there's a distance of 7 plus the distance to E is 9. That's not better than what I have, so I leave that H alone. Going to B, I have the distance to E, which was 2, plus 9. 11 is better than infinity. So we put that in there, and then that's it. And E is done. All right, we go to the next smallest that's not done. That'll be H. H is going to go on to our done list, and we check the neighbors of H. Now, we could get to E, but E is already done. G is already done. If we go to B, we get to H with distance of 3 plus this edge is 6. So that's better than what we had. So we put a 6 there, and the right way to go there would be H. That's it. We're done with H. The next smallest that we have is D with a distance of 5. And notice that's not this edge, it's this path here. So D has a distance of 5. We're going to look at its neighbors. And if we look at C, so we could get to C by going through D. We can get to D with 5 plus 3, so that's better than what we had. We're going to update C to be a distance of 8. Looking back to E, we're already done, and G, we're already done, so that'll be it for looking at D's neighbors. Now we have F, C, and B. The next smallest is 6, so that's the one we're going to look at. Alright, let's look at the neighbors of B. We have H, and we have E. Those are already both done, so we don't need to look at that. Next we have C and F. It's a tie, and we'll pick the smallest alphabetically as just a way to break the tie. It's not going to matter. We'll get the same values for the distances whichever way we break the tie, no matter what the graph is, if it's positive weights. Okay, so we're looking at the neighbors of C. We have a path to A, which we haven't been to yet. So we know the distance to C is 8 plus that 4, so we have a 12 here through C. We also have a path to F, which isn't listed as done yet. We could go 8 to C plus 2. 10 is not as good as what we already have, so we leave that alone. And then C has edges to D and G, which are both already done. Alright, that's it for C. Now we would either go F or A. F is smaller, that's 8. So we're going to look at the neighbors of F. F has an edge to C, which is already done, an edge to G, which is already done, an edge to A. So I'll pause and ask you, if we went to A through F, what would be the distance? What would be the distance to A if we go through F? Alright, we have a distance of 8 to F, and then we would add on the 7, that would be 15, and that's not as good as what we have already. So we leave that alone, and we're done with F. And then the last one is A, and we would look at the neighbors of A, but everything else is already done. So this would be our shortest paths. And if we want to draw these, let's draw these. So I'll start at G. Let's make this orange and thicker. So let's see. That's where we started, and for each of these vertices we have where it came from. So A came from C, B came from H, C came from D, D came from E, E came from G, F came from G, G was the start, and H came from D. And that is those are the shortest paths. So the shortest path to A from G goes like this. Shortest path from G to B goes like this. Okay, so this algorithm is put another text box, let's see, over here with some other notes. Okay, so it's guaranteed to work if there are, if all the weights are non-negative. As long as the weights are non-negative, it's supposed to work. And note produces a tree. There'd be no reason to, well, in this instance, it produces, right, this produces a tree. There'd be no reason to have a cycle in here, so this does produce a tree. The running time is linear-ish. It depends on the exact way that we store all this information, but the number of times that we have our main loop, so the main loop is we take the smallest distance to the smallest distance to a vertex that's not done yet, and then look at its neighbors. So that makes us look at, consider each vertex once in the main loop, and all of the edges get considered as well. So we're going to consider each of these neighbors, and depending on how we look at things, each edge is twice. So it depends on being able to keep track of the smallest distance. We need to keep track of smallest distance and update the distances. So as we go, we have to update some of the distances and keep track of the smallest one. A good data structure for that. Heap is good at keeping track of the smallest of something and updating values. Alright, so that's Dijkstra's algorithm for finding the shortest path from one vertex to all the others. That's one of the algorithms we're supposed to be able to do. So I could ask you, given a graph and a start, draw the shortest paths that Dijkstra's algorithm comes up with. Alright. Now we'll go to do this again. We're going to pause. Okay, so this was our Dijkstra's algorithm. If you want to pause on that, to think about that, go ahead. Otherwise, we're going to move and do minimum spanning tree. And we'll keep track of some things here. This is going to be Prim's algorithm for minimum spanning tree. Okay, so a tree, so quiz for you. For this graph here, how many edges will a tree have that spans this set of vertices? So spans means includes all the vertices. And how many edges will we need for that? One way to do it would be to take A here and go around the outside. 1, 2, 3, 4, 5, 6, 7. So seven edges. So n minus 1 edges in general if you have n vertices. And minimum means lowest total weight. This only makes sense for weighted graphs. If the edges don't have weights, then you need n minus 1 of them, and that's it. Alright, so we're trying to find a minimum spanning tree, and the basic idea is start with some vertex. Let's say we start with D. And add the vertex, the smallest edge, to ones we already have. Okay. So I'll keep track of our tree. What do we have so far? Our total weight. And things we still need to add. I'm going to start with G. Total weight will be nothing so far. Maybe I'll put for each vertex here, I'll put where it came from. Alright, we want to add to G. So far we still need A, B, C, D, E, F, H. Alright, so we need everything else except for G. The smallest edge from G to something else is to E. So E, I'll put in parentheses, we got there from G with the weight of 2, so we have the total weight of 2 right now. And I'll, as we go here, because this is, as we go, I'll make a note of the ones that we are keeping, like that ones. Alright, so the next step is we have G and E. So what's the smallest weight coming out of there that adds something new? There's two different choices. G to E is 3, G to H is 3. Either one of those, let's say we break ties by taking the smallest letter. If that's the case, then we would take G to E. Keep that here, that we have G now, which we got to from E with a weight of 3, and now our total weight is 5. Again, we have two choices. We could add H with a weight of 3, or we could add C with a weight of 3. We'll break the tie by taking the smaller letter, and we'd add this one. And so we add C, which we got to from D with a weight of 3. We now have a total weight of 8. Now we have C to F, which is 2, that's the smallest. So we'll take that one next. For a weight of 2. We got the F from C with a weight of 2. Our weight goes up by 2 more. Now the G to H is the smallest. That grows us. Okay. So we'll add that in. So we add F or H here, which we got to from G with a weight of 3. We're at 13 now. All we have left is A and B. We can get to B with 3 now. Add in. Now we have B, which we got to from H, and if we were keeping track of what we still need here, all we have left is A, and 4 is better than 7, so we would add that vertex in. So we have A from C with a weight of 4. And we add 4 more to the weight. We're at 17 unless I forgot to count something. Let's make sure. So we have 6, 9, 11, 13, 19. Let's try this again. We've got 6, 8, 14, 16, 20. Modulo being able to add numbers. Alright, so that is a spanning tree. There's no cycles, and it's the smallest weight spanning tree in this graph. There could be more than one spanning tree with the same weight, but we're guaranteed to get one of them that is smallest weight. If we compare the spanning tree that we got from doing Dijkstra's algorithm, this is not necessarily going to give us a smallest weight spanning tree, and if you add up the weights, I think you're going to get something larger than 20 here. Okay, so this gives us the shortest path to each vertex. Shortest path to F is 8 here, but if we're just looking for the total weight to get all of the vertexes some path, that's pretty wasteful, and that's a big difference between these. So what we get for the shortest path versus trims basically is from getting rid of this edge and taking this cheaper one in this case. Alright, so that's Prim's algorithm. Let's take a look at the list of things you're supposed to know about graphs. Okay, you're supposed to also know that a complete graph is a graph with all possible edges. You can search for that, complete graph. So this is a complete graph right here with 7 vertices. It's an undirected complete graph with 7 vertices without self-loops. Alright, so complete graph has all possible edges. There's that. And a bipartite graph is a graph where you can separate it into 2 parts. Let's take a look at this one. Can we separate this into 2 parts so that every edge goes between the 2 parts? You would try to do something like drawing a line like this, and do all edges cross that line? No, they don't. There are edges down here. So we want to make left and right, and make it so that all edges go from the left to the right. No within the right and no within the left. That's not true here, and this graph is not bipartite because we have a triangle. If you have a triangle, there's no way, or just this one here, there's no way to split this left to right so that all the edges are from one side to the other. No matter which way you draw the left and the right here, you'll have an edge that stays completely on the one side. We'll look at a picture of a bipartite graph. Okay, there are some examples. So here I can draw a line straight up there, and all the edges go from the left half to the right half. There are some other examples of bipartite graphs. And I think that's good enough for you for graphs. Good luck on the final. And have fun.